Swayam Prabha. Digital India. Educated India.
Friends, today continuing on the topic of gradually varied flow, we shall be discussing one of the most important topic of gradually varied flow, that is the computation of gradually varied flow, which we will be requiring in our almost day-to-day life when we talk about engineering life, means in computation of hydraulic engineering. In many projects we required this computation of gradually varied flow, and we will be taking up that particular topic today. And let us recapitulate what we have discussed till now on gradually varied flow before going to the computation of gradually varied flow. Well, we have discussed till now that classification of gradually varied flow, that we have discussed very elaborately. Then we did discuss the characteristic of different type of gradually varied flow. For each of the different types we did discuss how their characteristic varies, and then we have discussed another important point, that is the control section, how the control section influences the gradually varied flow. I mean, when it is subcritical flow, then now we know that control will be on the downstream side. When it is supercritical flow, then we know that control will be on the upstream side. Any disturbance created at upstream will influence the flow in case of supercritical flow, and any disturbance created at downstream will be influencing the flow if it is subcritical. So that sort of discussion we have done. Then we again could see that how the flow profile forms over a series of channel, means channel connecting channel, but with different slope. In nature actually this will be a continuous channel, but the slope will be changing from point to point, and that is what actually we get in practical field. We hardly get a slope which is uniform all through the channel reach. So that way we will be getting channel where the slope will keep on changing, and so that sort of channel when we are getting, then how flow profile is forming. So that part also we did discuss in the last class. And now with this introduction to gradually varied flow, we shall be moving on to computation of gradually varied flow. Okay. Well, by computation of gradually varied flow, what we really mean, we can just in a systematic way say that computation of flow depth of gradually varied flow profile at any section of a channel, that can be regarded as computation of gradually varied flow. Then we know that gradually varied flow, I mean when we are talking about computation of gradually varied flow, what are the things we are covering in this particular discussion, that we must know. That we know that gradually varied flow can be steady and as well as it can be unsteady also. Now in this particular topic we shall be discussing on computation of steady gradually varied flow. We are not talking about unsteady situation, that will take up in general when we will be discussing the unsteady flow. Well, then again when we talk about any flow system, then we can have one dimensional flow and two dimensional flow, And here of course when we are talking about gradually varied flow computation, we are meaning solution of the governing equation of one dimensional gradually varied flow equation. So, we have already derived the one dimensional governing equation of gradually varied flow, and we will see that how this equation can be solved. And when we refer to our earlier equation, if I just write down here, it was like this, that dy dx is equal to, it is SB minus SF divided by 1 minus q square t by GA cube. So, when we are writing this equation, then this particular equation is of non-linear type. This differential equation is non-linear type, because this dy dx is on the right hand side, we are not getting this as a function of x only. This is rather a function of y, because SF, that is the friction slope, or say top width, or here the area, all these are basically function of y. If it is non-prismatic channel, then only we will talk about that these things are also varying with x. If it is a prismatic channel, all these are pure function of y. So, that way what we are getting, that right hand side of this equation is function of y, and that is why this equation is a non-linear differential equation, and we cannot get a direct analytical solution of that. It is difficult, and that is why we go for different approaches for solving this particular equation. And that is why in gradually varied flow solution of gradually varied flow equation, rather for obtaining the gradually varied flow profile, we go for different method, and all those method of course give us approximate solution, as we cannot get it analytically at any point. Exact solution we cannot get. So, these are all approximate solution. So, these solutions we can list in this form. You can just refer to the slide. That is, first method which is popular is called direct step method. Well, then we will discuss about this in detail of course, and then we have another method that we call standard step method. What is the basic difference between these two methods? Well, here just to initiate, we can say that in direct step method we divide the entire flow profile into some steps and then we solve, and the steps, that is the say distance or length of the entire flow profile, we divide it into some smaller length, but these smaller length are not fixed, that we get after computation only. We will be getting that, first we will assume that this is the depth, and then we will be getting what the corresponding distance for this particular depth. So, that way the distance or the small segment that we will be getting are not of fixed length. But in standard step method, here also we divide the entire flow profile into small segment and then we solve. But here we first divide the channel into our required small section. If we want that, we want to make it very small, we will make very small. If we want to make that okay little bigger, we will make it bigger. Well, now why we will make it smaller or bigger section? This has definitely something to do with the assumption that we are making in deriving the equation and in solving the equation. So, that will be coming later. Then we had some graphical integration method. Graphically we can integrate this equation and we can get a solution for that. Then we have direct integration method. This direct integration means in fact for some of the value we will be using some table and then we will get a solution for this particular equation. In fact, several approaches were there for using this direct integration method. Different people started and they gave different way of solving it by using table and chart. But nowadays these two methods are just becoming a historical importance, because nowadays we have computer and we can go for lot of other advantageous technique for solving, and rather than taking recourse to some graphs, rather than taking recourse to some tables, people do not go for those solutions. We go for some solutions which we can have using computer programming. So that means that these methods are nowadays becoming almost obsolete and we do not use. That's why in our discussion we will not be discussing these two methods we are not discussing, okay. And then we will be discussing the method numerical solution. Well, that means apart from standard step method and direct step method, we will be talking about numerical solution. In fact, this direct step method and standard step method is also one kind where we put some numerical value and we get the solution. But by numerical solution, what I mean, for solution of differential equation in general, several numerical methods have been developed so far, and I am just listing some of those which are generally used. That is, one is called Euler's method, which was used earlier. Then of course, when it was found that this method is not giving very accurate result, then improved Euler methods was used, or it came. Then again, to improve upon that, modified Euler method has been suggested, and so people are using this method. And then Runge-Kutta method, as we know that this is a very popular numerical method, the fourth order Runge-Kutta method. This gives very accurate solution for gradually varied flow profile. So that way, these are of course general numerical methods that give solution for any differential equation of the type that dy dx, for any equation of the type that dy dx is a function of say x and y, then any of these method can give us solution. Of course, I am just naming a few only here. There are several methods. Then of course, for solution of gradually varied flow, particularly, I mean these methods, out of these methods, solution for gradually varied flow, this was trapezoidal integration method. This is nothing but of course modified Euler method, and that was applied by Prosat in 1970 first for solution of gradually varied flow, and that's why I am just putting it in a different, under a different heading, that developed particularly for computing gradually varied flow, okay. Then always we find that there are some drawback in these numerical methods, particularly in numerical method we based on a known value at a particular point. Suppose this is the curve. If we know a particular value at this point, say initial value, then based on the value here x0, we compute the value at x1, say what will be y1. Suppose y0 is known, we calculate y1. This is say initial value problem sort of things. We are getting this one here and we are trying to solve this one. And in numerical method, we calculate this value for a small value of say delta x, and this delta x, if we keep very small, then almost all these numerical methods what I have stated here will give accurate result. Now if this delta x value is increased, suppose delta x we are taking very large like that, this is our delta x, then some of these methods will give erroneous result and some of these may still give correct result. But now the main problem is that what should be our delta x, and then we could see that for computation of gradually varied flow, as the flow profiles are very large, and then people may wish to put delta x to be when suppose it is a 6 kilometer, then people may feel that okay, let us keep delta x as 10 meter. Someone may feel that okay, let us keep delta x as 100 meter, and in that process when we are using a computer program, if we give some delta x value, this will give us a solution, but there may be some error introduced in it. So we tried to develop another method which can give us correct result even if our delta x is significantly large. Well, so that method we named as improved numerical method. Well, about all those methods we will be discussing briefly under this particular topic. Well, now when we talk about computation of gradually varied flow, our first approach is to determine the type of profile. Okay. So, how to determine the type of profile, that is our first step. So, a problem once it is given, then first what we should do as a step, first that calculate yn, that is first we should calculate normal depth. Okay. Then we should calculate critical depth, then we should calculate critical depth. YC. And for normal depth calculation, we know that computation of normal depth we have already covered, so we are not discussing this here. Similarly, for calculation of critical depth, that also we have covered already, so we are not discussing it here. But we know that we need to calculate Yn and Yc. And then, based on the statement of the problem, or based on what we are observing in the field, or say situation we are expecting, suppose a dam is there, we know that dam height is something, or say a weir is there, we know that weir height is something. So, the flow profile will have to cross that, means what will be the depth of the flow profile at any section, that we must know. So, we must know what will be the depth of control section, depth of any section in the flow profile, that we will have to know, that we will have to know, and that may be control section also. Well, that way once we know these things, then we have that relation, if it is, if our Yn is greater than Yc, and if that depth, what we are knowing that from our other references, that this will be the depth of flow profile at a particular section, if that y is greater than Yn and is greater than Yc, then we will be knowing that this is, first from this part, that is when Yn is greater than Yc, this will give us that this is a mild slope. Well, if, and then when we get this sort of relation, this will give us that, combining this plus that, what we will be getting, that this profile is M1 profile. Well, so first we, to know the type of profile, we need to know that what type of bed it is, comparing this Yn and Yc. If Yc is greater than Yn, then this will say that it is a steep slope. And suppose we are getting a depth y which is greater than this one, which is greater than this one, then it will become, if we just add this part, this will become S1. And similarly, for some other condition, oh well, let me write it this way, that is, this is suppose S, this is giving us, and then if y is greater than Yc, then it is actually, then it is S1. Then suppose if y is less than Yc, but y is greater than Yn, these two combination if we give, this will give us S2. So, like that we need to compare the value of Yc, Yn and the known depth of the flow profile, one of the known depth, and then that way we are getting what the type of profile is. Similarly, if the slope is horizontal, that also we need to see, then it will be S type of profile. If it is adverse slope, then it will be A type of profile, means it can be A2 or A3 depending on the value of y that we know from the control section value. Okay. So, that way first we need to determine the type of profile, and then we can move for solution of that particular profile. And for solution, first let us discuss this direct step method. Okay. Well, this direct step method is a very simplified approach for solving gradually varied flow, and is very popular because it can solve the profile if almost correctly if our channel is prismatic. And for a channel in nature, we can many a time assume that to be prismatic if the variation of width is not that much within that portion. Well, let us see what the very basic theory of direct step method or how these are used. Well, let me draw a channel portion. Say this is the bed, and suppose this is the flow profile, okay. And I am drawing this as y1 and this is say y2. Now let me consider the datum to pass through the downstream point, this, and let this distance, we are considering a small segment. This is what actually basically drawn is a small segment of the profile. Entire profile is quite large, so we are considering a small segment. Well, that we are giving us delta x, and this slope is nothing but bed slope SB. This is nothing but bed slope SB. Okay. Then there will be velocity, so say v square v1 square by twice g, and that will lead to total head somewhere here, and here say v2 square by twice g. This will lead to total head here. I am not considering alpha, that is the velocity coefficient here, but anyway, this is the energy gradient line. This line is called energy gradient line, and slope of this line is nothing but SF. Slope of this line is SF. Now, if I draw this line in this direction, extend this line, horizontal line, then we will be getting that this much is nothing but the loss, and we can write this as delta x into SF. And similarly, say this particular extent, what we can write, if this is the delta x and SB is there, so this distance will be delta x into SB, delta x into SB. Okay. Well, so the energy level between two sections we can write in this form. Here we are of course considering the loss part in the form that this is delta x into SF it is coming, and we are considering the loss is only due to the frictional loss, and that is what we are getting here. And energy slope is also like that we are drawing. This is the energy gradient line, okay. Well, now if we just write the relation between the section 1 and 2, what we can have, that is total, if you see this is also horizontal line and that is also horizontal line, so this part is equal to, I mean from here to here is equal to from here to here. So we can write equating the energy level at 1 and 2. Basically we are equating energy level, means loss part also we are including here, and that is why we are talking. Otherwise this energy level here is definitely higher than energy level here. Energy level upstream will be higher than energy level at downstream, but we are writing this delta x SF here. So what we can write, that delta x SB plus y1 plus v1 square by twice g is equal to delta x SF plus y2 plus v2 square by twice g. Well, now we know that one very popular expression for y1 plus v square by twice g, that is nothing but energy, specific energy. Well, so we can write this as, this implies that delta x into SB in plus the specific energy E1 is equal to delta x SF plus the specific energy at E2. Well, now from that what we can have, our target is to find out that what is the delta x when y2 is the depth here and y1 is the depth here at upstream. So, I mean, knowing the y1 and we know the y1, suppose we want to know what is y2, then we know that at what distance this y2 will be. So, that way we are trying to derive one relationship between this distance we want to find out in terms of the known parameter at this and at downstream, at upstream and downstream. So, let us write it as delta x. Now, we can write delta x is equal to say E2 minus E1 divided by SB minus SF. So, this indicate that this is equal to, we can write the energy loss delta E divided by, this is equal to SB minus SF. Well, so from this expression, this because our this delta E is the basically energy difference between this upstream and downstream point, and SB is the bed slope and SF is the friction slope. Now, one point here is very important, that although we are talking about SF, this SF at the section 1 and section 2 will not be same, it will not be same value, but we can compute this SF using Manning's roughness formula or Chase's roughness formula. But whatever way we calculate, in fact, we will be getting two different value of SF for section 1 and section 2. And so, what SF we will be using for computing the delta x, that is one important point, and that delta then for computing this delta x, in fact, we should use the SF as the average SF between the section 1 and section 2. So, how we can write that delta x is equal to delta E divided by SB minus SF bar. This SF bar is what? SF bar is equal to SF1 plus SF2 divided by 2. Now, what is SF1? That we can write, say, Q is equal to 1 by n A r to the power 2 by 3 SF to the power half, that we can write. So, what is SF? That we can write as Q square n square divided by, say, A square r to the power 4 by 3. So, knowing the value of depth at a particular section, say SF1 means everything, Q is fixed, of course, Q square, and n, if we consider n to be say constant for any depth or for any section, suppose roughness is not changing significantly, then we can consider this to be constant, and then area, that will depend on depth. So, if I talk about a section 1, then this will be A1 square, and hydraulic radius, again it will be R1 to the power 4 by 3. So, this way we can calculate, putting everything for section 1, we can calculate this particular value, and then SF2 we can calculate everything like Q square n square A2 square R2 to the power 4 by 3. Now, what it indicate? Now, if we want to calculate this delta x, we must know, similarly for energy calculation also, energy, suppose energy difference calculation, we need to calculate y1 plus v1 square by twice g. Similarly, energy at the level 2 or section 2 will be y2 plus v2 square by twice g. So, we need to know the information about a particular section. Well, so what is done, say if we want to calculate suppose gradually varied flow. Say this is the flow profile. Now we have calculated first yn and yc, and then we know that this depth is known, say y0. So we know this control section depth. So we have got this value. Now what we can do from this known value, initially we are knowing one value, and from this known value what we can do, we can calculate this SF1, say. Then okay, I am writing this as 1, say. From this we can calculate this SF1, and we can calculate this Y1 plus V1 square by twice G means E1 we can calculate. Then we actually do not know E2 and SF2, that we do not know. So what we assume, that first we assume okay, we want to calculate the delta x, but we do not know where this delta x will be. But let us assume that the depth y2 will be the depth, and so we need to calculate now, and of course from our knowledge of gradually varied flow, knowing the yn and y2, we must know whether the flow profile will be rising or falling. That we definitely know. If it is in zone 2, it will be a falling profile. If it is in zone 1, it will be a rising profile. If it is in zone 3, it will again be a rising profile. So that part we know. Now from that, suppose we know that it is a rising profile, and that way if this depth is y1, then we can say, let us consider, we will compute our delta x for a depth y2 which is at upstream. Okay. So this y2 we are considering from our side, and we want to know what will be the delta x, or that at what distance from y1, that is x1, suppose this one, and this is suppose x2, at what distance from x1 this x2 will be, which correspond to depth y2. So taking this y2 as our known parameter, we are calculating SF2 and we are calculating E2. So everything we are calculating, and then we are calculating what is our delta x. So once we calculate delta x, say let us put this delta x as delta x1. So what we have got after calculation, say y2, for y2 we are getting this is delta x1. That means our purpose is served, that we know that our y1 depth is at x1, then after delta x1 distance our y2 depth will be, that we want to know. If we want to plot the profile also, now we can plot up to this point. But then again we can calculate the next depth is suppose y3, next depth is y3. So that also we will be first considering from our side, and we will try to calculate delta x2. Well, delta x2 means the other things are all remaining same. Now we know e2, so e3 we need to calculate. That means this difference between e2 and e3 will be our delta e. Then we can calculate SF2 here, 2 means SF3 we can calculate, and that means just following the same procedure that we have adopted for computing from here to here, we can now, knowing this y2, we can compute this distance delta x2, which will correspond to another depth that we are considering from our side y3. So this way we are calculating delta x2. And if it is m1 profile, suppose from our first we are calculating what is yn and yc, and we are getting suppose this is m1 profile, then we know that this profile will be extending up to yn, up to normal depth yn. So we can keep on computing this one. Suppose this yn value is, we know that yn is equal to suppose our 10 meter, or okay, let us this is 5 meter, and this depth is suppose 10 meter. Then we will keep on computing our depth, our distance, by reducing the depth. And to what extent we will compute that, because we know that this profile will be coming up to 5 meter where yn depth is. So we can take our last depth, which is little higher than yn, maybe 5.1, suppose 5.1 meter. So last depth, suppose we are taking let me write as a ym, suppose the last depth we have taken m number of section, and last depth we are taking after breaking this part, last step we are taking, suppose this is delta x m minus 1, because for each of the pair we are getting one delta x. For y m number we are getting, say, our pair, we are getting m minus 1 pair. So, this last extent will be delta x m minus 1, and then we are getting a distance here. So, if we sum up all this delta x, summation of all delta x, so this delta x I is starting from, say, 1 to m minus 1. If we do that, what we are getting is the total length L. Total length of the profile L we can get like that. And at different distance, what will be the depth, that we are already calculating like this. So, this is what the procedure for calculating gradually varied flow profile in direct step method. I have shown if it is M1 profile how we can compute. If it is M2, the same procedure we need to follow and we can just calculate. Okay. Now, let us see this application of direct step method. I have already explained, and perhaps further explanation is not required at this level. So we have seen that how we can compute a gradually varied flow profile using direct step method, but this method has some limitation. Well, what are those limitations? We must know, otherwise we will end up applying this method into a situation where actually this method is not applicable and we may end up in error. So, let us see what are the limitations of this particular method. First, I must say that this method is applicable in prismatic channel only, applicable in prismatic channel. Why? Well, this is one limitation of this method. The reason is that, say, when we are calculating, say, y1 is known, we are calculating y2. Rather, we are not calculating y2, we are assuming y2, and then we are calculating this delta x. And the equation what we are using, the governing equation, basically there itself we made one assumption that the channel is prismatic. Okay. Now, when we are applying that equation and we are solving for delta x, so we do not know beforehand what is the length of this delta x. After taking this y2, we are calculating this delta x. Now, it may happen that channel is, suppose plan view of the channel is like this. Plan view of the channel is like this. When we have, say, y1 at this section 1, and then we took y2, because we do not know, we thought that y2 may be somewhere here, and that is why we thought that this part is prismatic and then more or less prismatic, and then we, thinking in that line, we took the y2 value and we started computing the delta x. But when we finally computed the value of delta x, we are finding that delta x is coming here, and we do not have any control on that. And that is why basically we have computed from 1 to 2, this depth we have computed, but in the process, as we did not know the delta x beforehand, we have ended up in computing this between two sections, between which we cannot at all consider the channel to be prismatic. This is a non-prismatic type, and so what calculation we are doing, this will be definitely erroneous. So, this is one limitation. And second limitation is, of course, there. Second limitation is that error increases with increase of delta x, this is of course a with increase of delta x. So, this is a error which is common for any this sort of numerical methods, and here also it is say when delta x is very large, then this error is there, error increases. Why? Because say actual flow profile is, well, let me draw another diagram here. Say in between we are using, suppose the flow profile is, or the energy slope line may not be straight. Suppose energy slope line is like this, energy slope line is this. Well, this is not the flow profile is somewhere here. This is suppose the actual energy slope line between these 2 points, and then what we are doing, that we are calculating energy slope at this point SF1, and we are calculating energy slope at this point say SF2, and then we are taking average of these two, SF1 plus SF2 divided by 2, we are taking average of these two, and that we are taking as SF bar. Well, and that SF bar is being used for computing the gradually varied flow. Now, this will be valid when this change of slope between this point and that point is not that large, and say whatever we are taking, we can suppose average value is representing the change of slope between this point and that point more correctly, then only it is applicable. Otherwise, this will end up in giving some error, and we do not know actually in this particular computation, we do not know what our delta x distance is beforehand. So, after calculation only we are getting this delta x distance, and as such how much will be this part, that is our SF1, SF2, how much this will change and how this error will introduce, that we are not knowing beforehand. So, this method is having this sort of limitation. Always we should take the y1 and y2 in a way, that is y1, that is next value of y2 in a way that our delta x becomes small, and that of course will have to have some experience based on the type of profile, based on the shape of the profile. We need to decide how much we can reduce the next y2 value, or if it is a rising profile or if it is a falling profile, how much we should increase this. So, that way this needs some understanding, and if we find that delta x is becoming very large, that means we should know that we are introducing some error. We can again redo the entire work, putting smaller value of change in depth. That is, say if I say delta y is the change in depth, then from y1 we should reduce y2 by a very smaller value, and we should see whether our delta x is reducing or not. That way we should calculate. Well, these are the major limitation of direct step method, and because of these limitations, particularly this standard step method came. Well, in standard step method, what is the basic difference between direct step method and the standard step method? This is that in standard step method we can decide our delta x, we can fix the delta x, and then we calculate the y. Of course, here one disadvantage is that as we are fixing our delta x, and as the equation says that we cannot have directly the value of y, so it will require iterative procedure. Trial and error will be required in calculating the depth y2 corresponding to the depth delta, corresponding to the distance delta x. So, that is what one limitation is. But with having lot of computational facility now, all high speed computer, that cannot be considered as limitation. Iteration can always be done quickly now. Well, just to say about the very basic theory of this particular standard step method, now you can concentrate into the slide. What we can do, say we can write the energy equation between two sections, say section 1 and section 2. We can write the energy equation as, say it is Z1, this is Z2, this is H1, this is H2, and then we have V square by twice Z, V1 square by twice Z, V2 square by twice Z. These are there. We have then energy gradient line, and this is bed slope is there. Well, and then there are definitely some losses in between. Well, now that part now we can write as, say, energy level at upstream side, say equating the energy at section 1 and section 2. What we can write that Z1 plus H1 plus V1 square by twice G, that is equal to Z2 plus H2. Well, here for depth we have written H, no problem. Earlier I was writing Y, here anyway it is already written. H we have written anyway. Z2 plus H2 plus V2 square by twice G, but definitely these two energy cannot be equal, because loss part we need to add here, and in this part we are adding two type of loss. One loss is due to friction, say SF, that is SF from the friction slope itself we can directly get this SF, that is our, if the distance is very small delta x, then we can get the friction slope SF multiplied by delta x. But apart from that friction loss, there are some other type of loss also. In between there may be eddy formation if there is some changes in the channel pattern, velocity is also dropping, suppose significantly from V1 here to V2 here, and then because of that change in velocity there may be another kind of loss that we call as eddy loss. Okay, that's why that loss was also added here as HE. Well, and that's why this particular method, that is a standard step method, has another advantage of using this for a non-prismatic channel also, because this sort of eddy loss are prominent or important in case of non-prismatic channel. If the channel is expanding or if the channel is contracting, then this sort of eddy loss are important or significant. But if it is a prismatic channel, then this eddy loss is not that significant unless there are a lot of turbulence and other. Well, and that's why in direct step method, that was also another reason why we cannot apply it to non-prismatic channel. There we didn't consider this eddy loss. Okay. Now, what is HF? That we can write that HF we can write, if this distance is delta x, if this distance is delta x, then we can write this as SF into delta x. Okay. And then what is HE? Head loss. I am not drawing here. Okay, I can draw a horizontal line where this will be, and total loss we can divide it into two parts. One is, say, this part is HF and there is another part which is HE. Then eddy loss, that eddy loss can be written as some factor K, then of course V1 square minus V2 square divided by twice C. So, whether velocity is more here, less here, does not matter, we need to get the difference. So, that way this expression can be used for eddy loss. And then experimentally it was studied and it was found that this K value we can use as 0.1 to 0.3 for a contracting channel. If the channel is contracting in the downstream direction, that is like this, flow is going like that, then we can use this value between 0.1 to 0.3. Of course, what it should be, whether it should be 0.1 or 0.3, that will depends on your experience, but anyway we can take in between. And then it is 0.2 to 0.5 for expanding channel. It is used like this for expanding channel, that is when channel is expanding like that. That means it is clear that this eddy loss will be more when a channel is expanding and then rather than in contracting. So, that part is very obvious from this particular value, and this point we need to take care. Now, of course, still in standard step method, we generally do not prefer to go for a non-prismatic channel all along, but still wherever necessary we go, and then in that case if some expanding portion is coming, then we can use this Hg value there, we can calculate this value well. And then from this equation what we are getting, if we write this as the H1 head H1 plus say this as the head H2, sorry, this is equal to, we can write this is equal to H1 equal to H2 plus the loss SF plus H, that we can put under bracket. Well, now using this relation, how we can calculate the y1 and y2, that is our required point. That is, suppose if it is y1 we want to calculate y2, or say this is this is y1 and we want to calculate y2, then how we can do that. And this can be other way also, we can have y1 here known things and we can calculate y2. Of course, here one important point is there, if we are computing from the downstream side to the upstream side, that is of course important. If we are computing from downstream side to the upstream side, say our first known point is at downstream and unknown point at upstream, then this SF plus HE, that is loss, we will have to deduct from here, then only we will be getting this value head at here. So that way we can use a plus minus sign and we can write it accordingly. Well, to have some better understanding how we actually calculate, use the standard step method, that we can see through this table, you can refer to the table. Here we have one advantage. Okay, let me just take this slide and let me show you. So distance means, how we can do it, distance means say our starting point is 0 and then we are continuously computing the profile, say first distance is 50, second distance may be 100 increasing by 50, but the next distance there is no restriction, that we suppose find that okay next distance we will take 200, then there is a gap of 100 between, and here is a gap of 50, here also a gap of 50, it does not matter. So distance at any point we can calculate. Now based on this distance we will have to decide what is our small delta x or dx, that is we are getting, we could write it as delta x also. So this is, for this part actually we are writing dx is equal to 50, say, from here 0 to 50 we are getting this is as 50, and then for this 100, 50 to 100 this is again 50, then from 100 to 200 that is basically 100. So this way we can write the delta x. Then we can put what is our bed width B. So again if it is a non-prismatic one, then bed width here from 0 to 50 and bed width here may be different. So that way we can write the bed width value. I am not putting any value here. Then similarly Z, based on the slope, bed slope and this distance, we can find out what is the rise of the bed or what is the fall of the bed, that Z value we can write. So Z1, Z2, all this we can write this. Then suppose at a point, first point we know the H value, so that is known, and giving double marks mean this is known. Then for this known value we can calculate area. Then once we calculate area, then if our q, it is we are doing for a particular q, so this velocity is also known, So when we know these things, that we know the h and v, then we can calculate this energy at section 1, that is h1 plus v1 square. So that we can calculate h plus v square, if I do here v1 square by twice g, that we can calculate here. Okay. So this is known. Then from this all these value we can calculate what is the perimeter at this point, we can calculate what is the hydraulic radius at that point, because area and perimeters are known. Then we can calculate SF, friction slope, as I have shown already. By using Manning's formula we can calculate the friction slope. But what will be the SF bar, that we cannot calculate at this point. Then we will come to this table, this line again. Then for this delta x we are calculating this B value. Well, this is basically Z plus, just 1 minute, here this energy means actually we are talking about this Z plus H1 plus V1 square by twice C. Okay. Similarly, this E2 is also. So, because Z value we have calculated here. Then for this part we will be putting again the B value and Z value, then H value, what we are rising, how much we are rising, that we will be putting here, then H, then area we know, V we know, this part we can always calculate, and then coming here we will be calculating the SF bar. How this SF we are calculating here and the SF we are calculating here, between this 0 point and 50 point we are calculating both the SF. So, this SF bar will be basically average of these two values. So, combining this we are calculating the SF bar. Okay. Then we can calculate SF, the friction loss. Once we get the SF bar, then we can calculate the friction loss, SF bar into delta x, that we can calculate. Then once we know the V1 and V2, here this is our V1 and this is our V2, this is our V1 and this is our V2. So, taking that V1 and V2 we can calculate what is the energy loss, and then if we sum up these value SF, HE, and then here what is our Z1, then Z and H and V square by twice Z, all these things will give us the calculated value of E2. Now, as per our relation that E1 should be equal to E2. Okay. And of course, as I was telling already that if suppose E2 value is, we are calculating for a upstream section, if this value we are calculating for a upstream section, then we should see that whether this value minus this two value is equal to this particular value or not, that we need to check. Or if say E2 is at, if E1 is at in the proper direction, that is actually that it is in the upstream and this is in the downstream, then we can calculate in the same way what we are doing. But say if E2 is, that means the second section, suppose this 50 is at upstream, you just try to see this point. If this 50 distance is at upstream of 0, then only we should do E2 minus this part, and then we should check whether it is equal to this one. If 50 is at downstream of 0, then this way we should check whether this is equal to that. If it is not matching, then we should consider another H value, because this H value we are assuming, and then we should consider another H value, and then we can calculate all these value again, and then we can try checking this value, and in a comment we can write whether it is correct or not. Say first is incorrect, then second we are checking it, maybe again incorrect, then we will go for another trial, and finally after some trial we will be getting, suppose it is correct value. That means we take that for the 50 days distance, this is our, this H what we are taking is the correct H, this is the correct H. So, then we will go for the next 100 and we will follow the same procedure, and the energy E1 will take this one corresponding to the ultimate H what we are getting as the correct, and we will keep on computing, and this process will follow, and then we will be getting the depth at different section. These sections are already known. Now, when we talk about the applying standard step method in non-prismatic channel, what is the advantage? Say our channel is like this, suppose the channel is like this, and then it is like this. See, now our profile can be this one. Say this is the profile. We are giving a barrier here, and then because of this barrier, flow profile is forming like this. And suppose it is a M1 profile, but we want to compute it. So what we will do, say we can take our section here, then another section we can take here, then we can take another section here. Okay. So now our sections are like this. We are computing, this is our delta x1, this is delta x2. That way what delta x we are taking, that we are knowing beforehand that these are our delta x, and we decide that okay, this part to this part we cannot take, this portion is say more or less we can consider this to be prismatic, so let us take this delta x3, and then these are expanding quickly. Although we use a factor k for computing eddy loss, but still it is better to make a smaller section when it is significantly expanding, so that we can have other assumption that we had for prismatic channel, and that can be valid for this part. So that we are considering as a smaller part, and then we are calculating, and from here to here suppose our this is more or less prismatic, and we are dividing it by our own way like that. So this distance can be much larger, and that way we can compute our profile from here to here, considering different delta x as per our wish, and so that we can have a better solution and a more accurate solution. What the only problem is that we need to go for little bit of trial and error, and with a computer program this can be very easily overcome. So that is not, that cannot be considered as a big problem. Well, so this direct step method and standard step method were developed long back, and then people are using, and of course nowadays with the development of high speed digital computer we go for numerical methods. And in this particular class we will not be going for all those different types of numerical methods, but still we will be discussing some of the very preliminary aspect of numerical methods, how error get introduced in numerical method, to overcome those error, how we can use different types of numerical method, that we will be discussing, and with giving a brief introduction to the numerical method for computing gradually varied flow, we will be moving on to rapidly varied flow. So we hope in the next class we will be covering these numerical methods, and then we will be moving on to the rapidly varied flow. Of course before that we will have to take up some numerical problem, giving example of practical situation. Thank you very much.